All are joined.
Good morning, sir. Yes,
Good
yes,
morning.
sir.
You can start, right?
Yes,
There are
sir.
only three,
They
only five
they
are
are
there.
joining, sir.
Okay. 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 Just let's rewrite what we have done so far. Okay. So we first had mass equation. So let me write that. Put it as list them here. Okay. So governing equations. I'll put it for governing equations for ideal fluid without viscosity. Okay. So first we had these things you remember. Okay. First equation is equation of mass conservation. So that if you take it, so this rho density, so partial derivative with respect to this, and the divergence of dot product with rho u. Okay. So this is exactly what you have seen in the transport theorem. Transport theorem also, right? So what we do is this is the one, and second one, differential form only we are going to keep as of now. Okay, remember only these two. So this is your first equation. The second equation is, so this, if you want to do it or equivalent form, dou rho by dou t into a gradient of dot u, right? So that is your, what is in terms of capital D? D rho by dt plus, what is that equation?
Plus,
Grad rho, right?
yes, sir.
Plus rho into del dot u. Whatever that
Grad, yes, sir.
that
Del dot u plus.
grad rho into u, it will be absorbed into this capital D. So this is equal to 0. So this is another thing, right? This is another thing. So these are this. Now you have the conservation of momentum. So
Yes, sir.
momentum is that you have already seen that rho into total derivative du. So all these u's are basically your vectors. So what you have is dou u by dou t equal to minus grad p. P is function of scalar function of x, y, z, and t plus what else you have? So rho into, so external force. What is this actually? External force is what? What is that we assumed? B is body force per unit mass. For each unit mass, so that's why rho into B bar, that's over full omega. So this is what you remember. Okay, these are the two. This is the equation of mass. This is from mass conservation. This is your momentum equation. How many unknowns are there here? Still four more to join. Where are they?
Sir, I have informed others also, sir. I don't know why they are not joining.
These two. These two, if you look at this equation, so in the process of derivation of this, okay, so in this we derived transportation equation. That is two forms we can write something similar to what we have here, what you see here. So first equation is here. So the transportation, what is that? In the derivation of the momentum equation, you actually derived transport equation. What it tells you is total derivative. So rate of change of time over this Wt, or it can be even, yeah, this moving fluid element Wt into rho f, rho into f is any scalar function dv. This derivative I take it inside, that is actually your transportation theorem. So that comes out to be over Wt rho into, so when you have rho f, rho into the total derivative of df by dt into dv. Okay, so this is one version. Or what else you have? So d dt of
It's
same thing.
without F,
So let's take this as
without rho, sir.
rho f as g is a scalar function dv. Then what you see is wt. This inside simply you will not have this one. This is the usual df by dou f by dou g by dou t plus divergence of g into u. This you remember. So this something looks like your
Uh,
mass equation.
so,
First mass
so
equation, if
last
you have, yeah,
so last time you have written, sir, capital D F by dt plus dou into ju for this one.
which one? First one or second
The
one?
second one, sir, second one.
No, that's what I'm writing now here also, right? This is the
Here,
divergence.
sir, here is a you written dou g by dou t, and last time you have written capital dg by capital dt, something like that.
Lecture 10 or 9? Last one, right?
Last one, sir. Yes, sir, last one. If we take at a place of rho f only f, then formula become like
Rho u in the place of rho u, you have a f. Okay. So
yes, sir,
I'm trying. See, this is another version I wrote, right? Another version of transportation theorem I wrote in the bracket, right? Then where did I write this one? That is actually conservation of
sir.
momentum. So, yeah,
Yes, sir. Okay, sir. Okay.
fine, no?
Yes, sir. Fine.
Yeah, this is the same. See, to remember this transportation thing, you look at this first version of mass equation. That is inside for any function g. Okay, for any scalar function, for any f, scalar f. Okay, scalar function f. For here also for any scalar function, for any g, a scalar function. Okay, so these are the equations so far we derived. So in the process of momentum equation derivation, we derived these. This is your actual transportation. Transportation is in the process we derived. Okay, just while so actually you could have derived this transportation theorem separately, like the moment this is equal to this one separately, but the argument is same. So these things are separate. This is our the transportation equation. Transportation theorem from Reynolds. Okay, Reynolds transportation theorem. So you write it separately as a theorem if you want. Okay, write it this as for any scalar function if you want to do. So where do you start? So if you actually see the last lecture, so you have to start. Where do you start actually? So initially when you start, no, so yeah, 27th, yesterday's lecture. After that, first third line you have no ddt of wt rho u bar. So there you replace u by f. Okay, and then simply work out instead of vector function u bar, you work out like any function, any f function of x, y, z, t. So that is x cap of t. So this f is equal to any scalar function f is f of this one. Similarly here g of xt. Okay, scalar function basically. So if you do that, you'll derive this Reynolds transportation theorem, and then using this, that's what the left hand side rate of change of momentum you replaced with this right hand side of transportation theorem, which is equal to whatever the forces that are right hand side. So what you wrote is by transportation theorem to write ma. Okay, ma I am writing it like ma I am seeing it as time rate of change of momentum, r which is equal to m into a in that integral over the volume. That is what is the transportation theorem. That if you use it and finally right hand side forces, if you write it, put it everything is under the volume integral. So whatever inside is has to be, both sides has to be same. So that's what is our momentum equation. So these equations, if you actually see, what you see, what are the unknowns here? Rho is unknown, U is unknown, isn't it? What are
Yes,
the
sir.
unknowns here?
Yes, sir. Rho
Tell me
and
how many
U
unknowns?
and
Rho, U,
yes,
and
also, sir.
P. P is also known. P. Where is F? F is different, right?
Yes, sir.
F is something, you see, this is true for any F. That is not your fluid equation. This is like mathematics. You simply write, you derive this one in the using the same proof for any F. Okay, this is like a transportation theorem is entirely independent. So from your governing equations are only 1 and 2. Forget about this in the process, in the derivation of this, you use this transportation theorem. The proof is same. So proof, I just put it together. I could have written this first, saying that this is the theorem. First you derive it, then use this to derive the momentum equation. So when you look at this 1 and 2, the unknowns are rho u vector. So vector means u vector means you have three components, u v w. U v w in the u bar vector, and then rho is a scalar function, and then p is a scalar function. That's a pressure. That thing you don't know. So body force, usually whatever you have is a gravitational force or some other force, if that will be normally given. If nothing is given, so it's under the gravitational force. So that is what you take it as, what is a gz or something you take here, b bar. Okay, rho g. Okay, so it will be rho g z or something. So we'll see that one. So that when you consider this, b bar is basically force. That force you have to write. But see how many unknowns you have, how many equations you have. You have first equation will give you one equation, right? First equation is only one equation. Second equation is actually vector equation. You have three unknowns, u, v, w. First equation only one unknown, one equation, but unknowns anyway four, right? Five. Total five unknowns, but your equations are only four. You have three equations here. You have one equation here. Okay, one equation, and this is three equations. Okay, but for five unknowns. What are those? Rho, P, U, V, W. U, V, W. So these are the unknowns, right? So you need another equation to solve this one, isn't it?
Yes, sir.
So for even ideal fluid means what? We are only not considering the viscosity. Okay, so without viscosity, you have these equations. So you need another equation that comes from uh, conservation of energy. Okay, the third equation is actually coming from conservation of energy. So third equation, that if you derive and see, you will see this one, conservation of energy. Okay, so this is the third equation that takes care of another equation. Okay, so before I do this one, I think last class we have not finished that part. So let me go to that part. All have joined now, at least. Yeah, they are all there.
Yes, sir. Yes, sir.
See, if you look at this, what we have is this one. Uh, this is what you have seen, no, last class. So you start here, okay? Last class, you instead of row u bar here, for example, here in this row u bar, if you replace with row f, you repeat the same calculations, whatever you have done here for u bar, okay? So what is that you get? I have this Jacobian, that is just change of variable formula, d dt as it is there, okay? So why it goes to dou dou t inside? Because w is fixed. Once it is fixed, it is you are seeing it like Eulerian way. Eulerian way means only x was the domain is everything is fixed inside. So only x is fixed, x bar is fixed. Only time is only there. So that's why it has become dou dou t. But the variables are there. X, Y, Z are variables, but they are not depending on t. So you see them as only dou dou to t. So you seeing them as independent variables. So that is what is this. So now you expanded it. So instead of rho u bar, you have rho f, and here also rho f into that one. But this dou dou t of the Jacobian will be there as it is. So and you see here, and this dou dou t we replaced with total derivative. What is the reason? Now these are varying, no? Now at time t you are seeing that rho u at time t. Once you are inside, basically they are all time t. Okay, at time t inside, overall it is basically same only, no? This your change of variable formula. So now these are now varying with time. So that's why the dou dou t is nothing but you have to take the total derivative. When you take the total derivative, if x y z, if you are fixing the total derivative, dx will be there, dx by dt. Now it is not a function of t, so it is 0 earlier. Now you have x and y, x y z are varying with time t. So that's why total derivative when you write it becomes this Lagrangian way that or Eulerian way, you will get your both are same. Okay, so some people say if you are following the time, then you say that this is Lagrangian total derivative, okay, or material derivative. So you write capital D by capital dt. This you see some people, some textbooks it may be mathematically you can write d dt, simply d dt. That's your total derivative. Okay, and then what you have next is you have used this Jacobian. This Jacobian thing, we use this one. This is what we were trying to prove. Then if you assume that, if you substitute, finally simple calculations will give you your equation, your momentum equation. Whatever you have, momentum equation is here. So basically, left hand side of the momentum equation. This is your left hand side of the momentum equation. This is what you have. Okay, so the left hand side of the moment equation is the right hand side of the transportation theorem. That is what we wrote here. There's also one version of transportation theorem, but instead of any function f, you wrote rho u bar, okay, rho u. So simply do the same calculation up to here, and you see that rho u you replace with rho f. Instead of u bar, you put it as f, and you will come to the same conclusion. So you will see that that is what actually your transportation theorem. So, and then you can also do the same thing with instead of rho u, instead of replacing rho u by rho f, you put rho u itself as f. Then you will see that it's another version of transportation theorem. Okay, so only left hand side of this only we have done so far. So whatever the derivative outside dt, time rate of change of momentum, we put it as inside the volume integral. So some total derivative of some u bar. Okay, that is what you have done through transportation theorem. That is your MA. Primitive way you have written MA. Now F you have to replace like earlier. F is like surface forces and also external forces. Surface forces gives you surface derivative, surface integral, that you convert it into this type. Okay, that's what you have done during the initially when you derive the differential form of conservation of momentum. So do the same thing. So you'll have this one. So without doing so, once you convert this as this one, what you are getting is actually your integral form. So or you put it as a surface integral, that is also that's an integral form of conservation of momentum. Okay. Now if you convert this into uh, actually, you see here, see here in this, once you convert this into this surface, this volume integral, we use the divergence theorem, isn't it? Can you just recall when you define uh, divergence theorem we used, right, to get your surface forces F dou W. If you look at the earlier lecture, so what you get is that grad P thing. That is where we used divergence theorem. So strictly speaking, we said we should not use the divergence theorem and arrive it. So without using, if you do that, this actually you should write it as F dou WT. You should not write like a divergence theorem. So here you should not write like a volume integral. So before volume integral, what you have? Minus integral dou WT. This gradient of P, instead of this gradient of P, what do you get there earlier? Hello? Pn, right? Pn ds, isn't it?
Yes, sir.
That
Yes, sir.
PNDS you have to put it, then that is actually your conservation of momentum in integral form. So that we have not assumed any differentiability of the integrants inside, whatever the momentum, all the rho u, all those things. Okay, so you should not, if you really don't want to use the divergence theorem, so that is actually you call it integral form of the conservation of momentum. So actually, strictly speaking, though I wrote here conservation of momentum in integral form, this is already in the integral form. But this first integral on the right hand side, we use the divergence theorem. So before using the divergence theorem, you have to put it. Okay, so try to correct it if you want really integral form. That is what is the integral form. Next step is this one, whatever we wrote. Okay, this you have to replace with minus integral dou WT P into n cap ds. ds is surface area. Okay, so that should be the integral form conservation momentum. Then you use the divergence theorem again to that, and then assuming that all the integrants, whatever is differentiable, then you end up getting this equation, whatever we put it in this bracket. Okay, then this is true for every WT. So that is again you get back your differential form. Okay, this is exactly what we have in your conservation of momentum in the differentiable. This is what we write it as the equation, as a differential equation in that today's lecture, lecture 11. Okay. So in the process, what we use this one, this is the proof we need. So we were doing this one. So this Jacobian, if you look at this Jacobian left hand side, the derivative you take it inside. You know that j means zeta x zeta y. You are seeing as x of t is nothing but, or p of x of fixed x comma t, that is nothing but uh, basically what you have, that you calling, it is also same as zeta, xi, eta, and zeta, three variables. Okay, so the Jacobian is I'm writing as in the form of uh, what is this, rows I put it, zeta x zeta y zeta y. Okay, first one, first function zeta, xi function, I'm just taking the derivative with respect to x y z, that is your first row. Second function eta, again you take the x y z derivatives, next is zeta. So this is your Jacobian. Now you are applying the dou t. So dou t means you apply first dou t, first your rows, every element in your first row. That plus, now you do it for second row. That is your second. Now the third row. You do this one. Okay. So now what is that we did here? Dou t. So you consider simply one element in the first matrix, dou t of zeta x. That is assuming that is a flow, is the variables, it's time it is moving, so it should be smooth in the flow, the spatial variables. So that you assume that, then you can rewrite this as a mixed variable. Mixed derivatives are same. Okay. If we do that, dou x of the dou zeta by dou t is nothing but x ddt of x of t, first component. Second component and third component will give you basically d capital X by is nothing but is your u. U is your dou zeta by dou t, dou eta by dou t, dou zeta by dou t. Okay, so these are all same. So this means what we have is dou x, where after moving in time, that is your x of t. Okay, so that's what you have. So similarly, dou t of dou zeta by dou y is also like this. Dou t of dou zeta by dou z is also dou z of u. So these things you try to, you don't see, you also expand this dou x of u, dou y of u, dou z of u, as because u is a function of three variables, xi, eta, xi, eta, and zeta. So if you do x, if you write, it's only one variable, right? Do x is a variable. You have another variables y and z also. X variable, if you do, you also have inside xi. Xi is a function of x, y, z. Eta is also function of x, y, z. So like that. So this is a total derivative when you write du. So that is du by dou z into d zeta plus dou u by dou eta into d eta plus dou u by dou eta into dou zeta into d zeta. So now you divide with dx, that is exactly your dou x. Because the t is there, that's why we are writing dou x, because there is another variable. That is why we are saying dou x. Otherwise, we have to write du by dx. Okay. So anyway, so this is how you get dou u by, that is dou t of dou zeta by dou x is nothing but this whole whatever we underlined. Similarly, dou u by dou y, that is your dou t of zeta y. Similarly, dou t of zeta z. This is what is all these things you try to put it in your first matrix. First matrix. So let's look at the first matrix. What is the first matrix that you have? So we'll just do this one. So first matrix. First matrix, I'm just trying to put the first matrix as, let me see exactly what I should put. Dou t in the place of dou t zeta x, I'm going to write it as dou u by dou z. So I need bigger space. Okay, this is your first matrix. Equal to, so the first element is dou t of zeta x, that is dou x of u, that, but dou x of dou u by dou x is nothing but that full expression u zeta. Okay, dou u by dou zeta into zeta x plus dou u by dou eta into eta x plus dou u by dou zeta into zeta x. This is your first term. And what else? What are the other terms? Eta x for this here, zeta x. Now what is the second column? First element. Again you write dou u by dou y. That is dou u by dou y is dou u by dou z into zeta y here. Okay, zeta y plus dou u by dou eta into eta y plus dou u by dou zeta into zeta y. And here eta y and here zeta y. What is the third one? Dou u by dou z. Okay, here zeta z, z plus dou u by dou eta into eta z plus dou u by dou zeta into zeta z. So careful. So this is your z. Okay. So here what you have? Eta z and here zeta z. So this is your matrix. What is this matrix? Can you now identify? Can you now split into three parts? This is if you split this into three parts, this, this, this will be one row. Okay, first matrix. Then dou u by dou z is common. So you have dou u by dou z, dou u by dou z is common. What is left in the, if you take this one, zeta x, zeta y, zeta z, eta x, eta y, eta z, zeta x, zeta y, zeta z. So that is nothing but your j. J where? After going to j where? X, not x bar. This is x bar of t dt of t. Okay, this is what you have. Because everything is a function of zeta, no? Zeta, eta are already at time t. Your fluid particle at time t. That's why we are writing like this. Got it? Hello?
Yes, sir.
What is the second? What is the second matrix? Dou u by dou eta is common here, here, here. But what is the row left? If you take dou u by dou eta out, Eta x, eta y, eta z as your first row. But the second row is also same. That is why it is 0.
Yes,
Dou
sir.
u by dou eta into
Yes, sir.
the
If
matrix determinant is 0. So first, by the way, these are not, they are simply determinant. No, J, no, this is the determinant. This is the matrix determinant. Okay. First determinant. You have to write first matrix determinant of LHS. This is the
third one
determinant.
also is zero, sir. Third one is also
Third one
zero.
also 0. So you write like this so that you remember some other time. Okay. Zeta, when you look at it, you understand easily. So this is finally nothing but dou u by dou z, j of, uh, what do you have? So I'm going to write it here as a phi of xt, phi of xt comma t. Okay. So this is exactly what you have. So instead of x of t, we are writing that phi. It's just some,
Yeah.
those are all same.
Yes,
So
sir.
this into the
Then
Jacobian. So
yes, the
similarly,
same we can write,
similarly,
sir, dou v by dou eta.
yeah, exactly. So similarly, second matrix. Okay. Second determinant, second matrix determinant is dou u by dou eta into Jacobian, same Jacobian, isn't it? So phi of xt,
Sir, dou u or dou v?
dou u by dou eta, right?
I
Yeah, that's eta.
okay, sir. I think, sir, dou v for second matrix.
Oh, v. That's sorry. That is v. You're right.
Yeah.
That is v.
Yes.
That is v. You're right. You're right. Dou u by dou t. This is your xt, comma t. Okay. And
Yes, sir.
similarly, third matrix determinant is dou w by dou zeta, right? Into same g, Jacobian, phi of xt, comma t. So what are those determinants that you am talking about?
We are proving like del by del t
Yeah,
Jacobian
these are the
equal.
determinants. LHS equal
Yes,
to,
sir.
these are all determinants. Sorry, these I wrote it as matrix, but you have to say determinant. Okay, these are all determinant of the matrix. Those are Jacobians, no? So this part is the third one. This is the second one. Third one. This is third one. This is second. This is third. This is the first one. So you, when you write all this, these things you have to put there. So this implies LHS equal to what you have. J is common. J comes out phi of xt t into dou by dou xi plus dou v by dou eta plus dou w by dou xi, dou zeta. Okay.
Yes,
So
sir.
what happens to the right hand side? So where is the right hand side basically? This is the one, right? So this is your x comma t. Okay, this into everything at after time t, no? So it should be, this should be function of t. So when you write x of t, j of x of t, yeah, we wrote that. That is understood. J of x of t is nothing but j of phi of this one, right? So x is not fixed one there. X is actually j of, j is fixed, right? Actually, j is fixed, right?
Yes, sir. Yes, sir.
J is fixed. So you cannot say, so you don't say simply this is anyway fixed here. That is only fixed only thing, no? Jacobian, right? So this should be only j of xt. Ask me if any question here. So don't get confused, okay? This is only xt, j of x comma t. We're trying to be little rigorous so that you
Sir,
remember.
if yeah, Jacobian j of xt is fixed, then why we are putting in del eta?
Which one?
P dot U of phi phi of xt, sir. In above equation,
Yeah.
sir, where we
So
have written dou of dou of dot t.
yeah, that will do you by do you see now what do you have? So you have a Jacobian that is fixed x comma t. Okay, and this is well defined. So because this is nothing but simply you have x is a that is Jacobian. No, zeta is a zeta eta. Sorry, xi eta and zeta are functions of fixed x y z and t. That is the reason we have these two variables, fixed x y z and t for the Jacobian. Now this is nothing but your determinant. This is your del. I mean divergence of UVW. No, so u vector. Now where is this one? These are functions of xi and eta zeta. What is the functions of xi and eta, xi eta and eta zeta? Those are
Phi.
nothing but your x of t, or
Yes,
you
sir.
say p of x fixed x comma t and
Yes,
then t.
sir.
Okay, so
Yes,
this is
sir.
x
Yes.
of t comma t. So this is exactly your right hand side. Okay, followed.
Yes. Yes, sir. Yes,
That is
sir.
what
Clear.
we used yesterday. Okay, so in the derivation of the momentum equation. So I just save it here. I stop this, and I will share you again that lecture 10. Okay. So today, whatever I did here, so I'll share it to you again. Others, are you following? Only Rishabh is responding. Okay, I understand. But what about you? Do you have any doubts here so far?
No,
No,
sir.
sir.
No, sir.
Fine, right?
Yes,
Okay.
sir.
So let me go back to that other lecture that I started. So that file we will do now. What exactly we do there? So we were doing. Now can you see? Yeah. So okay. So here, see, I started this. Those who come late, this is what we derived so far. So first equation is mass equation, either this or this. One of them you have to remember. Okay. So whichever way, easy way you remember. So this is u bar. Okay, there's a u vector. So that's your first equation. Mass conservation or first conservation. Okay, mass conservation or equation of what is that? What do you call that? Equation of mass, right? Continuity. Equation of continuity or mass conservation. Okay, that is your first equation. The second equation is momentum, conservation of momentum or equation of motion. That's your momentum equation. This is your second equation. Okay, so if you look at these two equations, first is only one equation, third is, because it's a vector equation, you'll have three equations here. But the unknowns are rho p u vector, that is uvw. Okay, so total 5 unknowns are there, but you have only 4 PDEs. These are all connected PDEs, right? Coupled PDEs, but you have 4 unknowns. So where do you get our third equation, fifth equation? That fifth equation coming from conservation of energy in the system. So that too we will see how we derive it. So before this, so in the process of this, whatever we have done yesterday, whatever I showed you some time back, I talked. So this is the transportation theorem. This is the separate entity that only left hand side of your conservation law. The derivative, taking the derivative inside, how it changes the integrand. So that is actually your transportation theorem. There are two versions that we have. You remember one of them because we do application of Reynolds transportation theorem. We'll try to use it for some simple things like finding some surface boundary conditions. When you derive kinematic boundary conditions, we can apply here. Okay. So remember one of them. So we'll do that. So to talk about that fifth equation, we use energy conservation. So energy conservation in general, we will not do now for this general inviscid fluid equations. Okay, so in inviscid fluid, we will not do this conservation because inviscid itself, you may have the temperature thing you have to involve. Energy means what? What is the energy for you? So energy can be because of the moment of the, so kinematic energy, that is half mv square, no? half mv square may be possibility, because when the fluid is flowing, it has a velocity. So it has that energy, half mv square, kinematic energy. And though you're not considering the viscous forces, but still the system may have some temperature. The temperature means some thermodynamical things that you have to bring in. So that energy we may not be considering here. So let us not do it. Let us do it at the end when we did viscous equations. Finally, when you include the viscosity, you have conservation of mass is same. Conservation of momentum equation alone we will modify. So that time we will do there also. We again 4 equations, 5 onwards. That is the time we will do that conservation of energy for general context, where you involve this kinetic energy, and then you have this temperature thing. Temperature thing. See, how do you get the temperature into the system? In the fluid, those fluid particles may know molecular level, they may have, when you have the heat can be generated. Once the heat is generated, or rather when the heat is in the system, heat is changing in, no, the fluid is at different times at different heating. Okay, that means you are giving the heat through the atmosphere, or from the outside you are giving, or inside it has to happen, means what? Those molecular level, it has to vibration, right? Some molecular level heat is basically a vibration of those particles, molecules. Molecule vibration actually kind of giving you basically the physics or chemistry, if you look at it, that is the heat. The heat is basically the fluid particles are doing some work, or uh, you give the heat from the outside. So without considering that heat energy, so if you want to do it here conservation of energy, we assume, if you assume, that is only possible for incompressible fluids. Okay, do you understand now this point? So you really want to do this one, the general conservation of energy, where you need to consider other energies also. Okay, so right now we will do only for incompressible fluids. You understand? So for that, you need exactly what is the meaning of incompressible fluids. Ideal fluids means what? No, there is no viscous forces. There is no frictional forces between the fluid particles. But it can be fluid, it can be gas, or it can be liquid. So when you consider liquids, volume will not change, right? So you consider some volume, over a time, it is a same constant volume, same volumes. That, after some time you watch the same fluid element, after some time it may be moving, but it will not change its volume. Same volume it will be having. That is why you said it is incompressible. That is the definition of incompressibility. Otherwise, it is like acting like that is what happens for the liquids. So if it happens for gases, for example, though you may not consider the viscosity is not there between the particles of gas, but still you may have that volume may be changing, no? So the volume actually changing there. So different. So once it moves, it may be volume may be changing because it is a gas. So keeping that in mind, that is what is incompressible. So that is what is compressibility. So compressible fluid or incompressible fluids both can be ideal fluids. So we are now separating. So for both of them, you have to derive conservation of energy, really, if you want. But we deviate, we restrict only to incompressible fluids. Okay. So we'll derive that when you do that conservation of energy for incompressible fluid, you actually see that what you derive the conservation of energy is nothing but your you can derive it from your second equation. You will observe that. Okay. So you are actually not gaining anything once you know this momentum equation. That from that you can actually derive your conservation of energy for incompressible fluids. So then where is the third equation? Where is that fifth equation? That fifth equation is nothing but your the moment you say it is a incompressible fluid, that crucial first definition is your volume is not changing with time. Okay, that is the first thing. Now that means what? That your density is not changing with time. That means capital D rho by dt. Okay, within the subclass of this, that is actually definition of your incompressibility. This capital D rho by dt. As you move with the fluid, the volume, if you see this, so for example, Wt volume will not change. Wt is a fluid element, right? That volume will not change with time. That is what is the meaning of incompressible fluid. So that is same as saying its density is not changing with time as you move with the time, as you move with the fluid. That is same as saying total mass, this what is this derivative? Material derivative or total derivative will be 0. Okay, and that means what? This rho into the scalar function into del dot u equal to 0. So d rho by dt equal to 0 is total derivative is 0, one equation, and this del dot u, whatever you left now, if this is 0, del dot u will become 0. That is what is the meaning of incompressible definition. So there are three definitions here. Either physically you give the volume is not changing, and the next level little mathematics you bring in terms of this density, this total derivative of the density is 0. Once you put your mass equation becomes this one, that is also equivalent. That is, then it becomes del dot u equal to 0. So you have two equations here in the incompressible fluid. Dou rho by d rho by dt equal to 0, one equation, and then del dot u itself is 0. That is a definition. These two, if you consider, then you will get your 5 equations for 5 unknowns. Do you understand this point? Confirm it. Then we will write it anyway, the same thing. No?
Yes, sir.
Others, please. So anyway, so we will do income, this one, conservation
Yes,
of
sir.
energy later later in general. We'll write it here so that you will understand when you read later on. So let me put it in words. So this for both for ideal fluid. Okay, so for ideal fluids, or what we write is here will be done, will be derived later for viscous fluids. Viscous fluids where it involves thermal energy. Thermal energy and other energies. Okay, what is other energies possible? Like magnetic field or whatever, other things. Okay, those things. But in this case, what will happen right now? Right now, what is it? Right now, I'm writing it here. So, but for ideal fluids, that means without viscosity, still thermal energy is still possible. Thermal energy is still a possibility. Okay, still you can remove it. Thermal energy is still a possibility. For example, liquid gases. Okay, let's put it like a compressible. For example, what is this? Non-viscous gases means non-viscous compressible fluids. So if you know the equation in this case, that means you have the equation here also, right? So right now it is not required. Okay, so for ideal fluid, thermal energy is still possible. So however, ideal compressible incompressible fluids, ideal liquid fluids, ideal incompressible fluids, we can assume that uh, only kinetic energy. We can assume that only kinetic energy is feasible. Okay. How do you write this one? To put it in words, we can assume that only kinetic energy in the system, okay, is possible. To write only is possible. Okay. You understand this point? Hello.
Yes, sir.
So that means we are only
Yes.
going to do energy equation only for incompressible. Okay. That is, we derive here energy equation only for incompressible fluids. Okay. So first of all, I need the definition of incompressible fluid. Okay, so start with many definitions. Let me put it like definition 1. Okay, so first fundamental definition is volume. Okay, volume of the fluid element that is in your language, whatever we have done so far, WT is constant in time. In time T, as you change T, still the volume is same. Okay. Now what is the other definition that you can give? If the volume is not changing, density will not change. No, density is same, isn't it? Density of WT is also constant, right? That is rho of is constant. So now we take that ddt of rho of x of t, y of t, z of t, comma t. That is the meaning of this, na? With changing with time. This is changing with time, no? Different times it's same. So this is like this is changing for all times. Rho at different points as you follow the particle. Initially at x, y, z. Now at time t, x of t, y of t, z of t, comma t. So time variation also may be there. Time, because of time, it may be moving. Okay. So that because the total derivative has to be 0. This is the meaning. So what is this meaning? If x and y, z are functions of t varying in the earlier in description or Lagrangian description, this is the Lagrangian description. Earlier in description, this is actually total derivative. D rho by dt. Both are same. Okay. So these are the two things you can give. So immediately third, what do you get? By mass conservation, mass equation, mass or equation of continuity. Okay. By the equation of continuity, or mass equation, right? What do you get? D rho by dt is 0, no? So rho into del dot u equal to 0. Implies rho cannot be 0. right? Rho is the density. So del dot U equal to 0. So these are the three meanings that you can derive. Okay. So finally, either this is true or this is true. Both are same. Okay. But to solve those two equations, we will see that you'll see that now. Maybe next class, what we see is equation of energy is nothing but you can derive it from your. We will derive the equation of energy for conservation for the incompressible fluids, but you will see that the same thing can be derived from the conservation of momentum. So that means it's basically it's not independent. Okay. So that means how do you solve it? So conservation of energy is actually supposed to be independent, but it means it's not. But you have only 4 equations and 5 unknowns. So here that first equation you replace with these two equations separately. Okay. Del dot U is one equation because the dot product. This is one equation. This is a scalar equation. So we have these two you will replace for the equation of mass. Equation of mass separately you give these two. Okay. So this is how you
Okay.
give
Okay, sir.
you actually solve those equations mathematically because the number. Okay. So do you have class now, or I can take a few minutes?
So we have class, sir, artificial intelligence offline class, sir.
Okay. Okay. I think I'll take next class. Okay. I'll give
Okay,
equivalent versions of incompressibility. These are the definitions you can take.
okay,
Okay.
sir. Okay,
So
sir.
maybe yeah. I will share you immediately that the modified lecture 10 and lecture 11, whatever we have done today.
Okay, sir. Thank
Okay.
you, sir.
See you next week.
Thank you, sir.